since we've got this measurement, rather than just looking at one case, because we might have gotten lucky on the one case, we can look over a 3-year period. The solid dots in here are pure observations, and the open circles are corrected are bias corrected. A perfect fork and better skill is as we go towards the middle right. This is a gauge relative efficiency on the horizontal axis, and then the bias on the right axis. You'd like to have a 0 bias and a 0 gauge relative efficiency. So you want to be as far to the right as you can, and the gauges give us exactly that. And it turns out that as we make these estimates more sophisticated, let me see if I can actually show this on at least one of them. It won't be easy. Okay, if you look at the 2 gray circles on the left, that is actually what's the nonpolar metric estimates. The rest of them are the polar metrics, and as we make those estimates more sophisticated and take more of the polar metric variables into account, the forecasts actually the estimates become much better and become much closer to truth. And so again, this will hopefully help us and shows us that for a long time period, this will actually work. The complexity of the models that we can develop based off of the reflectivity dramatically improves the thing. The yellow circles, or the orange, whatever color you think that is the most sophisticated, and ends up when we do the bias correction that it has a pretty good estimate of what the actual hydrologic output comes for over a very long period. So over a 3-year period, it's a good estimate of what's going on. We also have some new radars that can provide really unique looks at things. This is from last Monday. You guys missed that one. And this was a series of tornadoes that came through the metropolitan area and east of here. On the right is an experimental phased array radar reflectivity, and you can see the Hook Echo associated with that southern storm, and a little reflectivity ball to the east of that, which is actually associated with another tornado. The upper right of that, there's actually an embedded Hook Echo associated with the storm that destroyed the Love's Travel store on the east side of Oklahoma City. On the left side is velocity from those storms. And you can actually see the 3 little couplets that are actually 4 on this storm. You can actually see 4 spots where we have red, close to green, the standard thing we tell people to look for, that are all associated with tornadic storms. The bottom left one touched down south of the National Weather Center in Norman. Its initial damage is about 200 yards south of the building. When they sent out the little call for people to go to the storm shelter in the basement, in fact, very few people went. Most people went to the windows on the building to go look outside and see what was happening. You know, it's an occupational hazard. But the thing about the phased array radar is that it allows us, the NexRad radar collects complete information about every 4 or 5 minutes of a volume of the atmosphere. The phased array radar allows us to collect complete information about the atmosphere in about 1 minute. And actually to look at intense events, if you're really interested, even faster than that. In this case, they are actually using the phased array radar looking at the lowest 2 elevations from it every 8 seconds. And it's a phenomenal thing you can see, that you can do. It also allows us to do different things with the radars. And when we combine phased array and the dual polarization, it is very likely that our ability to estimate actually how much water is falling out of the sky will dramatically improve. Because we'll be able to look at 1 minute, we'll be able to look lower in the atmosphere than the traditional radars look, and be able to look if there's an event that's going on of particular interest. We can look at that event in incredible detail that will allow us to get a much better picture of what's going on. It's just a phenomenal resource. At the lab also, we've been experimenting with doing multi-sensor radar, or multi-sensor estimates using satellite data, radar data, gauge data. This is an estimate from the Severe Storms Lab's Q2 project from the Nashville flood for 24 hours, getting estimates of upwards of 10 inches of rain on the 1st of May, in a large area of greater than 3 inches, and at a detail level of just a few kilometers on spacing, to where putting those into hydrologic models becomes can become a huge improvement in what we can do with the hydrologic models. And this is being produced routinely. In the session, one of the breakout sessions following this, Ken Howard and Suzanne Van Kooten from the lab will be talking about this and some other experiments that we've been doing that will help us, hopefully, to improve the way we understand water falling in real time. These estimates are essentially available as soon as the data are collected, or as close as we can process them to that. I was talking about observations, and we're on the edge of dramatically improving the way we collect observations about precip. Well, forecasting is the next step. Instead of just looking at what's happened already, let's start looking towards the future and trying to make some forecasts on. We're interested in particularly in short-term forecasts, 0 to 48 hour, and then a little bit on even 0 to 1 to 3 hour forecasts for extreme events. And there are a number of things that are going on in the forecasting community that I think are of great interest. One of those is a set is just actually trying to find better ways to evaluate the forecast. Right now, we use some pretty simple tools to look at the forecast, and what usually happens is that when people who build models or make weather forecasts show them to users, the users go, well, that isn't how I thought the forecast was. The forecasts weren't as good as that, or actually this forecast that you didn't think was very good was incredibly useful to me. And we know historically that the usefulness of a forecast and the accuracy of a forecast don't necessarily match up. There are lots of cases where a more accurate forecast was actually less useful to the user than a less high quality forecast was, but that it had better properties to it. So user-based evaluation tools are a big thing. I'll show you one example of some new stuff that's going on in that. Some information from these sort of out to 2-day forecast ensembles from an experiment that's just been started this week, and then what the future of ensemble weather forecasting is going to look like. And we're talking about, in this case, very high resolution, perhaps kilometer or even less for some cases, using radar as input and running them really often for just a few hours, rather than running, even 10 years ago, if you looked at weather forecasting models, they're run twice a day, and you see output every 12 hours. And when I started in the business, that's what, you felt really good to have even that much information. And now we're talking about running models that you look at the output every few minutes, they're run every hour with new information. We'll show you some of those, what's happening with that. One of the things that started to happen, and this particularly came out of looking at precip fields, is what we call object-oriented verification. With the operational weather forecasting models that existed about 10 years ago, one of the problems came up is that there were some efforts made to improve the models and to make them work better. And what happened was that our historical traditional scoring systems invariably said that the traditional model, the old model, was better. Even though when you showed the new forecast and the old forecast to any human being above the age of about 2, they'd go, well, this looks a whole lot more like the weather than the new one looks a whole lot more like the weather than the old one did. And this was a real problem. And what it came down to was the fact that our traditional scoring methods were intended to look for really broad forecasts and really smooth forecasts. And the old models produced really smooth forecasts. So that if you actually cared about rainfall of more than 1/4 of an inch in a day, they were useless. But they were really good at forecasting light rain over a big area. And for some applications, that was actually useful. Well, this is one of the things that then led to trying to come up with ways that we could do a better job.